Hello, in this video we're going to keep going with chapter 10 and we're going to look at how to do calculus with parametric curves. Okay, so the first thing we're going to look at calculus-wise is tangents. And we're going to assume that these two functions are both differentiable, and we're going to be given some point on the curve. So you can still do a tangent as a function, but you just want to be able to do it at a certain point as well. So when we're trying to compute the tangents, we're looking for dy dt. And the chain rule, so y is a function of x, and x is a function of t, and y is a function of t. So dy dt gives us a chain rule. So it's dy dx times dx dt. We just rearrange this and solve it and get this nice formula for the derivative. So this, just looking at it, it should make sense, right? Just dy dt over dx dt. You can, the dt's are not denominators, but you can think of them that way if it helps you remember the formula. And so the idea here is that if we imagine a particle is just moving around in the xy plane, then dy dt and dx dt, those are just the vertical and horizontal velocities. And dy dx is just the ratio of the quantities, right? So the slope is how fast the particle is moving one direction versus the other. If dy dt happens to be 0, that's a horizontal tangent, as long as the denominator is not 0. And there's a vertical tangent when the denominator is 0, as long as the numerator is not. If both of these happen to be 0, then we don't have a method of finding the tangents right now. And we'd have to use other methods, like factoring methods, L'Hopital's rule, something like that. Now, for a second derivative, it's the same process. The chain rule gives us a dx dt over here when we take the derivative. And when we solve for that, we get an extra dx dt in the denominator here. This formula is harder to remember, so make sure that you memorize this. So the second derivative of y with respect to x is just the derivative of the first, what's the derivative with respect to t of the first derivative. But then you divide by dx dt because there's another chain rule that comes from this calculation. All right, so let's do an example that will tie together both of those formulas. So here we have a parametric curve. We're going to find the slope of the tangent line. Well, we're going to find the equation of the tangent line at t equals 1, and then we're going to find a second derivative. So dy dx at t equals 1 is just dy dt over dx dt. So dy, this is y, this is x. So you just take the individual derivatives, right? Very easy derivatives. Then we plug in t equals 1. And 2 divided by 2 is 1. And the point of tangency, so we need to find the point because we're converting to rectangular coordinates. So you just plug in f of 1, g of 1, right? So here's x down here, right? So you plug in 1, you get 1 minus 1 is 0, so x is 0. Here's g of 1, 2 plus 1 is 3, so it's 0, 3. Then you just use point slope form, and you get the line y equals x plus 3, and you're done. So real easy. Nothing real fancy is going on with this stuff. The toughest thing you might see is one of those situations where a point might have multiple tangents. Doesn't matter. You're evaluating this at t, not at x and y. Right? So the slope is given by the value of t, and then you just plug in the point. You plug in the slope in point slope form. So even if a curve self-intersects, you're plugging in the values of t, then you plug in x and y. So the slope is given by the value of t. All right, second derivative. Just use the formula, right? Real easy. and its quotient rule. So if you want to follow along with these steps, just pause the video as it goes. But I'm assuming you guys can do quotient rule. You're 2/3 of the way through Calc 2, so hopefully you've learned the quotient rule. And then I brought these denominators together because they're the same, so it just goes up a power. Simplified the numerator. Simplify the numerator one more step. Then I FOILed the denominator. And then I simplified by multiplying through by t to the 6th over t to the 6th. And it works out this real nice function here. Well, you might not think it's nice, but it works out really nice. So parametric curves have really, they don't get simpler as you take more derivatives, right? Where most functions get simpler when you take more derivatives, not necessarily parametric curves. All right, well, that's it for slopes. Now we're moving on to areas. So the idea here is we have a curve traced out by x equals f of t, y equals g of t. And t is just between alpha and beta. So what happens is we just use u substitution here. So y is g of t. dx is the derivative of f of t. So it's f prime of t dt. And then you just plug a into the equations to get alpha or beta. So those are usually given in the problem. Ordinarily, you're either given the values of t or the values of x or y. You just have to work backwards and find t. So remember, these are bounds in t. Whether it's an x integral or a y integral, doesn't matter. And notice that which one is alpha and which one's beta depends on the order of integration, because when you plug in the t values, like it might go from the top to the bottom, but we don't integrate from the top to the bottom. We always go from lowest to highest or from left to right. And if you happen to get a situation where x is a function of y, you're integrating in the y direction, so it's x as a function of y dy. You just switch the equations. So it's real simple. And then you would find the bounds for t the same way. So you got to memorize these formulas as well. But this is real formal. Once you see how the problems work, it's going to look just like the stuff from chapter 5. All right, so here's our function. And so I went ahead and made a graph, and I could see that. So let me go back up here and show you. We have to find the area between the region and the y-axis. So when I look at this, I need to find these two intersection points, here and here. And you ask yourself, is this going to be a x integral or a y integral? Well, this is definitely a y integral, because if I go up and down, I'd have to subtract the function from itself. We don't know how to do that. But if you go to the side, right, the integral goes up from the bottom, but we're going to do right minus left. So this function, this is the rightmost function. So the area between these curves is right minus left. So, but we're going to find the intersection points first. We just need to know where x equals 0, right? This is the y-axis right here. So I just set the x coordinates equal to 0, and I get t equals 0 and t equals 2. So I'm done. I have already found the bounds for my integral. But what I want you to notice is that as the integral would be done, we'd start at the bottom and go up. Right? And remember, the y-coordinate's given by square root of t. So this is radical 2 right here. 0 radical 2. But because it moves up, that is a x dy integral. So it's not side to side, it's up and down. And when you plug the values in, right, we have this like generic version of the formula, but there are two functions up there, right? There's a rightmost function that is a vertical line, and then there's a leftmost function that's a curvy thing. And because these integrals are done right to left, at least when you set up the integral, right? It's the rightmost function and the leftmost function. These bounds are in y right now, So you set it up as if it were a normal integral from chapter 5. Then you convert it to a t integral. So if you need to review how to do the area between curves, now's a good time to review that stuff, because on the homework, you might have to do integrals that are up and down or side to side. It's been a long time since we did areas, right? It's been since chapter 5, so you might have to go back and review that stuff. We did a lot of integrals, but not so much areas, right? All right, now we convert it to t. So the rightmost function, if you look at the graph, let's go back and look at the graph. The rightmost function is the vertical line that is the y-axis. Well, that's just 0, right? So that's where x equals 0. So you just write 0 minus x of t. So whatever the leftmost function is, it's going to be a function of time, because we're calling it leftmost here. And then dy is this whole thing. It's y prime of t dt. Notice the bounds of integration went back to t. So I set it up as a xy integral, then you convert it. You have to do it that way or you're going to make a mistake. So I just plug everything in. I took this negative out front. This is the x equation, and this is the derivative of the y equation. Right? I went ahead. I mean, it's just the y equation was just square root of t, easy derivative. But this is x. So I simplified. Again, very easy integral to do. You can do it by hand or on a calculator. Your homework requires that you type this in as a simplified fraction with radicals. So make sure you can fill in the steps between here and here, even though this is a Calc 1 problem from here. But if you're doing the homework problems or you're on a test and you want to like check it and see if you're getting close, you can always do the numerical integration just to check the numbers. Okay, now we're going to look at arc length. So in section 8.1, we saw that if capital F prime is continuous on an interval, then the length of the curve was given by this. Well, we can always just substitute in the x equals f of t, y equals g of t. And what we get a chain rule thing, right? Substitution rule. And what we're going to do is we're going to require that the dx dt is positive. The reason for that is we need to set this up as an integral that looks like something from chapter 8. So it has to either travel from left to right or right to left. So we're basically forcing it to go left to right by making the derivative of x with respect to t positive. So as time increases, the function moves to the right. And that means this thing can't double back on itself. Because when we do arc length, for example, let's say we had a circle, you're not allowed to like double up a function on itself, right? Because that would double the arc length. So we're just saying that, for example, if we did a circle, it would do the top half of the circle and have to stop. And then use geometry to do the rest of it. So what happens is, we already know the derivative of y with respect to x is this. But the chain rule here turns dx into dx dt. Well, we can actually bring this thing inside the radical, which might seem like a silly thing to do, but it's not. If you distribute this inside the radical, it cancels this, and then it squares. So this formula, the arc length formula, is actually easier here in chapter 10 than it was in chapter 8. It's just the individual derivatives squared. Take the square root. So that looks an awful lot like the distance formula. And it turns out it is, except these are rates of change. So you're sort of like taking the average distance between all these tiny little points, and it gives you an arc length. So it's pretty nice. So you'll see that these problems aren't too bad. They do require a ton of algebra skill. So I'm going to show you a problem. I'm going to show you how to do the algebra. All of the problems more or less look like this. If it gives you trouble, look up some problems on the internet or talk to me about how to do this, because you're going to have to do problems like this on a test. All right, find the exact length of the curve. So this is just some funny curve, and we just want to find the arc length. So went ahead and did both derivatives. These are both very, very easy derivatives. Now, the arc length formula has that dx dt squared, dy dt squared inside the radical. Let's take care of that first. Right? So we're going to take care of this stuff under the radical. We have to simplify it before we can proceed. Now, if you're just doing a numerical solving method like your calculator, you could actually just type this into your calculator and you'll get a decimal answer. But again, on a test, I may ask you to simplify first, then do the integral, and then further simplify. So let's see how to do that. All right, so got the derivatives. Now I'm going to square them. Then simplify. And it turns out this has to work. This is another perfect square. It doesn't look like one, but it is one. So this is another perfect square. Now the square and the square root cancel. The integral of this is just e to the t minus e to the minus t, and then minus 0, and you're done. So make sure you can fill in the missing steps on these when you do these problems. Oh, these are supposed to be negatives. So if you're writing this down or you printed it out, I'll fix the PowerPoints before I repost it. These are both negative 2t. All right, but let's keep moving. All right, so the last thing we want to look at is surface area. Surface area is arc length and then rotated. So you can see that here's the ds that we had from arc length in chapter 8. 2 pi y, that's circumference. And so all this is the circumference times the radius. I'm sorry, it's 2 pi times the radius. And the radius is variable, right? The radius is a function times the arc length. And that makes sense, right? That as you progress down the arc and you're going around in a circle, the radius is changing. It's a function. And we can still use the general symbolic formulas that we saw in chapter 8. And that's how we want to do this. So we're going to compute this part first, then plug it into this formula. If not, you just have these like monster formulas. We really don't want that. We want to keep these problems more manageable as we're working through them. All right, let's do one. So in this problem, I just want you to set it up, and then you can solve it on your graphing calculator, because it turns out we're not able to actually do this integral. Sometimes you can, sometimes you can't. In this particular instance, we don't know how to do the integral. So I did both derivatives, right? These are both product rule. Now I'm going to go ahead and just do that stuff inside the radical first. In example 3, it was manageable to do the whole problem at once. A problem like this, just due to its size, we're just going to simplify that part first. So you just square both derivatives, FOIL everything out. So this is all one thing. This whole thing here is this thing FOILed. Then you rearrange and regroup, and you get this. So make sure you can do these steps. You guys know what the kind of stuff I like to ask on tests. This looks like a pretty good problem, or something like it. So this is 1, sine squared plus cosine squared, and this is 1. So this thing simplifies really nice down to t squared plus 1. So when we set up the big integral, that's going to be in the radical. So there's our big integral. Right? So here's our y equals t cosine t. We already did this part, and it's given from 0 to pi over 3. So this is all given in the problem. We don't know how to do this integral. I mean, it could be something like integration by parts, but forget about it. Just do it on your calculator. You get 3.1 and you move on with your life. So this one is really just, can you set these problems up? And one other thing too that I want to point out. When we go back here, we're rotating around the x-axis. So just like in chapter 8, that tells us when we build the function, the formula, that this is going to be a y. If we go around the y-axis, everything else is the same, but this becomes x. Right? So if you need to go back and review chapter 8 before you do this stuff, that's fine. It's not always y. It depends on what axis you're going around, just like we did in chapter 8. And same with the other integrals we saw for arc length and stuff, right? We saw stuff like that. All right, well, that's it for this video. If you have any questions, let me know. And I'll see you next time when we talk about polar coordinates. All right, bye-bye, everybody.